through a few more examples of solving trig equations. I know yesterday we got a good start, and so it's good, to kind of go through and either watch or solve on your own, and then fast forward to see if you get the same solutions, or if you're absent, certainly you can catch the lesson in these examples as well. So the first example here, I'm solving a couple things I would like to notice, and it's a good way to kind of summarize, especially if you were here yesterday, is that I'm noticing 5 theta, a frequency of 5, right? So we talked about anticipating 5 times as many solutions. And over here, this tells me two things. It tells me I'm solving for the answers in degree mode. It also tells me that I'm only going between 0 and 360. And even though that's a limit, the frequency of 5 is still going to come into play, changing that wavelength. So I'm going to be taking that 360 and dividing by 5. I'll see here in a moment to get 72 degrees as my new frequency. So, or a new wavelength. So first, let's isolate cosine. So we're going to subtract 1, and we're going to divide by that 2. So cosine of 5 theta would equal -1, and then divide by 2. So we're looking for when cosine is equal to -half. Okay, so when does that happen? Well, cosine is -half in quadrants 2 and 3. So -half here. And so that would be a 60-degree reference angle in both quadrants. So that's 120 degrees and 240. So right now, 5 theta is equal to 120 degrees plus 360 degrees K. And 5 theta is equal to 240 degrees plus 360 degrees K. Now, remember, we should be mentioning that K is an element of the integers, but eventually we'll not need that because we'll have a finite number of solutions. So again, as a recap, 5 theta, that tells me I should get 5 times as many solutions. So instead of 2 solutions, it looks like I'm getting 2 times 5 or 10 solutions. Okay, now let's divide out by 5. So 5 equals 24 degrees plus 72 degrees K, or theta equals, oh my gosh, what is that? 48 degrees? Yeah, 48 degrees plus 72 degrees K. Now, remember, K is an integer, but since we have a restriction of just positive angles, it doesn't make sense for K to be negative. So we're going to choose 5 different K values, right? We're going to let K equal 0, 1, 2, 3, and 4. Those would be the first 5 non-negative integers, and we will get answers. So when, again, we're letting K be each of these values. So when K is 0, you get 24 degrees. When K is 1, we're adding 72 to that, so that's 96 degrees. When K is 2, we're adding another 72, so that's 168 degrees. And another 72, so that's 240 degrees. And then add 72 one more time, that's 312 degrees, if I did my math right. Now, if you accidentally added 72 more, you would get 384, which is 24 degrees plus 360, so we've reached our one trip around from that quadrant. Now here, again, we'll let K equal 0, so we also get 48 degrees. Add 72 to that, and you get 120 degrees. Add 72 to that, and you get 192 degrees. Add 72, and you get 264 degrees. I think I'm doing my math right. And add 72 more, and you get 336 degrees. And if you add 72 more, you would get, what, 408 degrees, which is exactly 48 degrees more than 360. So we found our 10 solutions. Okay, fantastic. Question came up if you accidentally did in radians. I guess that's not wrong, but we are looking to label that in terms of degrees. So just thinking about that. Okay, now number 6 looks simple. Two cosine functions. The problem is we are comparing apples and oranges. 2x is different than 6x. I can't combine them, right? I can't use a temporary variable. Although I might have an identity for cosine of 2x, I don't really have one for cosine 6x. So then we want to think about another strategy, and that's hiding right here. So we've got a sum or a difference, in this case, equal to 0. It'd be much better if it was a product equal to 0. So we're going to utilize these formulas that are on the previous section. And it looks like I have one right here that I can use, which would be cosine of alpha minus beta. Cosine of beta equals -2 sine of their average times sine of the difference divided by 2. So let's do it. So here my alpha is 2x. If I'm trying to like just make sure I understand this, and beta is equal to 6x. So as I use this particular formula, the first thing I'm going to do is do -2 sine of 2 plus 6, so it's 8x divided by 2, so sine of 4x times sine of their difference divided by 2. So 2 minus 6 is -4 divided by 2 is -2x. So that equals 0. So I've taken a sum that, or a difference that's equal to 0, and made it a product. So that helps us, right? We use zero product property. That's what factoring is all based on. A couple of things. One, I know that sine's an odd function, so that negative can come out in front. So I got -2 sine of 4x times negative sine of 2x. And those two negatives cancel, or you divide out to the 0. So basically, and we could divide this 2 across the other side too. So, I mean, maybe, like it's this times this. So the negatives cancel. So I have 2 sine of 4x times sine of 2x equals 0. And this lead coefficient of 2, if I divide the other side, it really is irrelevant. So I guess sine of 4x sine of 2x is equal to 0. Okay, now, here's the thing. Zero product property, right? So either this first portion is equal to 0, or this portion must be equal to 0. The same way a product is equal to 0. So sine of 4x equals 0. Sine of 2x equals 0. And so you gotta think about when do we get 0? Well, sine is 0 here and here. So, and I don't remember what mode did it say? I don't know if it did or not. It did not. Let's go radians. Why not? So, so I know that happens at 0 radians and pi radians. So first I can say 4x equals 0 plus 2 pi k, and 4x is equal to pi plus 2 pi k. And then I would want to divide those by x. So then I would get, by 4. So then that would tell me that x is equal to 0 plus, if I divide 2 pi by 4, I get 2 pi over 4, or pi over 2k, and x equals pi fourths plus pi over 2k. Okay, now, oh yeah, don't forget, most important thing, k is an element of the integers. And also don't forget, I haven't forgotten about this one. So we still have another, right? We still have another set of solutions over there. But a couple of comments on this first one. A lot of times students ask, is it necessary, not to use a crayon, sorry, is it necessary to leave that 0? No, it's not necessary. You could leave it or take it away, it does not matter. Second thing, sometimes your solutions are exactly opposite each other. And so when I'm looking over here at 0 and at pi, if they're exactly 180 degrees apart, or exactly pi apart, that means that you could condense your original ones. You don't have to, but you could, in theory, instead of saying these two things separately, you could combine them by just saying, well, 4x is equal to 0 plus every pi k. Because think about it. If you're at 0, you add pi, you're at this other solution. Add pi, you're here. Add pi, right? So anytime you're symmetrically across, it only works if they're exactly 180 degrees apart, you can condense the pair of solutions. And if that were the case, then you would just get one solution that represents 0 plus pi fourths k, where k is an integer. So either is fine. The difference of the first set is actually, it's a kind of a redundancy. It does not matter. either one's fine. So you could either answer just the red solution or the orange pair of solutions, but that's still only half, right? It's only half the solutions. So we also need to figure out when is sine of 2x equal to 0. Well, we're going to see some similar solutions because, again, no surprise, where sine equal to 0, again at 0 and at pi. So here we have 2x is equal to 0 plus 2 pi k, or 2x is equal to pi plus 2 pi k. And again, I've separated them. So if you do decide to separate them, that means x is equal to 0 plus pi k, and x is equal to pi over 2 plus pi k, where k is an element of the integers. Now, there again, I could have condensed those into one, right? So I could have said these two could have combined to say 2x is just equal to 0 plus pi k, so divide out the 2. So x could have been just written as 0 plus pi over 2k, where k is an integer, same thing, right? So either's fine, whether it's just the singleton purple or the green double. And here's the thing maybe you noticed. When your two coefficients within your functions, like this case 4x and 2x, those numbers are not relatively prime to each other. So the fact that they're not relatively prime means that you're going to get some overlap. In other words, you're going to be repeating some solutions. That's okay. It's okay to be redundant in this case. So realize that, like, I'm going to get pi over 2 out of this solution. I'm also getting pi over 2 out of this solution. Like, that's okay. It's okay to represent them more than once. Okay. And then if you notice number 7, I won't go through the video, in this video at least, but if you notice number 7, take a look what you have. Another difference that's equal to 0. So how do you solve that? Well, let's take a look at one of our formulas down here and bring that down a bit if I can, and realize that if I have the cosine of an angle minus the sine of an angle, oh, wait a minute. I don't have it here. Oh, did I forget that on the last one? It's very possible. Cosine. Wait, how did I miss that? Oh my goodness. Uh-oh. Mr. Brown, maybe we should go through this. If I can't combine it like that, oh no, what am I going to do? So if it doesn't combine, then we need to think of another way to do this, okay? This is cool. I'm thinking on the spot, how exciting. So then I'm going to have to take advantage of something else I know. And what do I know is sine of 2 beta. So let's rewrite sine of 2 beta with its double angle. So sine of 2 beta could be written as 2 sine of beta cosine beta 0. Okay, now I know where we're going, and maybe you anticipate this too, because we can factor a GCF out of these two terms, that GCF being cosine of beta. So that means we have a 1 minus 2 sine of beta equals 0. Okay, I was worried. I am 100% assured now. So we will solve this using zero product property. So either cosine of beta is 0 or 1 minus 2 sine of beta is 0. So we have to consider two solution sets. We're looking for all values, so we're going to be adding 2 pi k. So let's first think about when is cosine of beta equal to 0. And again, thinking about when is the cosine equal to 0, it's at pi over 2, and it's at 3 pi over 2. So I could keep them separate and say beta is pi over 2 plus 2 pi k, or beta is 3 pi over 2 plus 2 pi k. And that would also mean for k is an element of the integers. If you realize that, wait a minute, my solutions are exactly 180 degrees apart, that means these could have been condensed to just beta is equal to pi over 2. You always start with the first one, plus half the period, pi k, where k is an element of the integers. Again, you don't have to. I'm just showing you another way to express that. Okay, that's just the first solutions. Next, sorry, that was weird on my voice. The next one I need to represent when is 1 minus 2 sine theta, or beta, I guess, equal to 0. So again, kind of isolating things to get sine of beta is equal to, well, we subtract -1, divide by -2. So it looks like sine beta equals 1/2. And again, thinking about where does that happen? Well, it's in the first quadrant if you're pi/6, or it's in the second quadrant if you're 5 pi/6. So again, I'm thinking beta is equal to pi/6 plus 2 pi k, or beta is equal to 5 pi over 6 plus 2 pi k. And of course, we know that k is an element of z integers. Now, teaching point, I can't combine these two because they're not exactly 180 degrees away, right? If I'm over here, I would have needed something over here, which I don't have. Or if I'm, if I'm here, I would have needed something over here, which I don't have. So there are multiple sets of infinite answers, and all of them are needed. Okay. Well, I'm glad I went through that one. So let's just complete all of our notes on that page. Hopefully that makes sense. And moving forward, be careful. Look for factoring, and and hopefully you'll be set for the problems.